The final video for complex numbers part 3, is on complex number arithmetic. We're going to begin with some examples of adding and subtracting, which is probably the easiest of all the arithmetic to do with complex numbers. So let's take a look at the following. We're going to add or subtract as needed in the following example. Let's do example 1, where we have 4 minus I, and then we're going to add to that 3 plus 2I. Well, if you're going to add complex numbers, all you have to simply do is add like numbers, or add like terms, so to speak. I'm going to add the real parts, 4 and 3, to get 7, and I'm going to add the imaginary parts together, negative 1I and positive 2I. If I do negative 1I, add it to 2I, I'm going to get positive 1I, so it's just 7 plus I. Let's call that one part A. Let's do another one underneath it. Let's do B. What if I have 7 minus 5I, and I'm going to subtract 1 minus 5I. Here, we're subtracting, and I have to be careful here. I would do this the same way as if the i's were x's. We're going to simply add like terms. Before I do that, I'm going to distribute the negative to that binomial. So I have 7 minus 5 times I, and I have negative 1, and then that negative 1 times the negative 5i is going to really be plus 5i. If you add the like terms up, 7 minus 1 makes 6, and negative 5i plus 5i end up canceling out, so this actually turns out to be the number 6. Let's do one more where we're adding and subtracting. This one is going to be a little bit more daunting, but not a whole lot. If I have 6 minus the complex number negative 2 plus 9 times I, and then add that to the complex number negative 8 plus 4I. First thing that I'm going to do is distribute that negative. So I'm going to have 6, and if I distribute the negative to the negative 2, it'll be plus 2. Distribute the negative to the positive 9i, that'll be minus 9i. And then I'm going to just write down plus negative 8 plus 4i. There's no need to distribute anything on that one. So let's see if we can add up the like terms. 6 plus 2 is 8. But there's a common number there, negative 8, so it's really 8 minus 8, and these cancel out. Negative 9i plus 4i is just negative 5i's, and we are done with adding and subtracting. Let's see if we can do another example here of just multiplication. So let's multiply the following. Let's do a couple of examples. For A, I'm going to do the complex number, or the pure imaginary number, 5i times the complex number negative 2 plus I. Guys, all you really need to do is distribute, and I'm going to multiply 5i times negative 2, multiply real numbers together there to get negative 10 times I, and then if I do 5i times positive I, that's going to be positive 5, and then I times I is I squared. Now, recall, I squared is negative 1. So we can use the fact that I squared is negative 1 here and substitute negative 1 in for I squared. So I really have negative 10I plus 5 times, instead of I squared, negative 1. So now I have negative 10I, and 5 times negative 1 becomes negative 5. We don't want to leave our answer in this form because that's not in standard form of a complex number. We want to write the real part in front and then the imaginary part on the other end. So this is negative 5 minus 10i. Let's take a look at another example. Let's do B underneath here. If I have 7 minus 4i times a negative 1 plus 2i, we're going to treat this as if it were just two binomials that we want to expand by foiling. So I'm going to multiply the firsts together. 7 times negative 1 makes negative 7. and I'm going to multiply 7 times 2i. That's going to be positive 14i's. Then the inner terms, negative 4i times negative 1 makes positive 4i. And then negative 4i times positive 2i is going to be a negative 8. And then I times I is I squared. Let's see if we can add up the like terms here. I have the I terms in the middle, so I have negative 7 plus 14 and 4 make 18 i's. Remember, you leave that I term the same when we're combining like terms. And remember what we said I squared is, it's negative 1. So I can replace that I squared with a negative 1 on that last term. If I simplify a little bit more, I have negative 7 plus 18i, and negative 8 times negative 1 is really positive 8. Negative 7 added to 8 make positive 1 plus 18i, and it's written in standard form. We're done. I want to show you one last example before we do dividing, because this leads into division, or something we will need to do in division. Let's say I have 6 plus 3i times 6 minus 3 times I. We're going to do the same exact thing in FOIL, but check out what happens in this case. You might notice this kind of fits the format of a difference of squares factorization. Watch what happens. 6 times 6, 36. 6 times negative 3i, negative 18i. 3i times 6, positive 18i. 3i times negative 3, minus 9i squared. The middle terms cancel, and you're left with 36 minus 9i squared, which is really negative 1. So check this out. We get 36 plus 9, which is 45. The imaginary part completely went away. Who would ever think that when you multiply such ugly looking complex numbers together, you actually get just a real number? By the way, there's a special name given to this type of complex pair. These are called complex conjugates. Complex conjugates. And we're going to use them on the next example to divide. Let's take a look at example 3 when we divide. Let's do example 3. We're only going to do 2 examples of division. The first one, let's do 5 plus 3 times I over 1 minus 2 times I. So we have 2 numbers, complex numbers, that we are dividing, and we have to go about dividing these in a roundabout way. This is a little bit bizarre. Essentially, what I'm going to do is I'm going to get rid of the complex number in the denominator by multiplying by its complex conjugate. The complex conjugate of any complex number is you keep the real part the same, but I'm going to use the opposite of the imaginary part. So the complex conjugate of 1 minus 2i is really 1 plus 2i. So these are, that was a really ugly looking bracket. These are complex conjugates. Now, when you multiply complex conjugates together, something really nice happens, like we saw in that last example. The imaginary parts end up canceling out, and you're left with just the real part. So let me get rid of that so it doesn't look quite as scary. So I'm going to multiply 1 minus 2i by its complex conjugate 1 plus 2i to the top and to the bottom. Keep in mind, the value of this fraction is really 1 because the numerator and denominator are the same. So we're not changing the quantity of this quotient. We're really multiplying it by 1, but in the process we're going to transform the way it looks. So we got lots of foiling to do. I'm going to FOIL out the numerator times numerator and then denominator times denominator. Let's start with the numerators. 5 times 1 makes 5. 5 times 2i makes positive 10 i's. Then I have to do 3i times 1. That's positive 3i. Then 3i times 2i is going to be a positive 6i squared. I'm going to leave that for a second and concentrate on the bottom for now. 1 times 1 is 1. 1 times 2i, positive 2i. Negative 2i times 1, negative 2i. And then negative 2i times positive 2i is going to be a negative 4i squared. Notice how in the bottom these middle terms cancel, which is going to be nice. And since we're talking about the bottom, I can't help myself because it just simplifies so nicely. I get 1 minus 4, and then I squared turns into negative 1. So I really get 1 plus 4. The denominator is just the number 5. This is nice. In the numerator, if I add like terms, those imaginary terms together, 10i plus 3i make, what, 13i's. And then remember, 6i squared is really the same as 6 times negative 1. So I get minus 6. If I add the like terms of the 5 and the negative 6, I get negative 1 plus 13i over 5. Now, we're not done until we write this in standard form. So I'm going to divide each term of the numerator by 5, giving me negative 1 over 5 plus 13i over 5. This is my real part, and this is the imaginary part. And this is the result when you divide those two complex numbers that we started with. Kind of cool. We'll do one more quick example. Let's let this be example 4, just so you see a little bit different look. If I have negative 1 plus 2i divided by, let's say, 5i. What is the complex conjugate we can multiply the top and bottom by? Well, think of this 5i as 0 plus 5i, right? So the complex conjugate is going to be 0 minus 5i, which ultimately is the same as negative 5i. So let's multiply top and bottom by negative 5i, the complex conjugate. If we do that, all I have to do is distribute the negative 5i to the numerator. If I multiply negative 5i times that negative 1, that's going to be, what, positive 5i. Negative 5i times positive 2i is going to be negative 10i squared. In the denominator, 5 times negative 5 is negative 25, and I times I is going to be an I squared. Let's see if we can simplify. The numerator will be 5i minus 10, and then remember, I squared is the same as negative 1. In the bottom, we have negative 25, and then I squared is the same as negative 1. So the numerator becomes 5i plus 10. The denominator is really positive 25. Now watch what we got to do here. I'm going to rewrite the numerator as 10 plus 5i. Remember, the real part comes first, then the imaginary, over 25. And then don't forget, you have to divide each term of the numerator by the denominator so we have it in standard form. And I can reduce these fractions in this case. 10 over 25 I think reduces to 2/5. And then 5 out of 25 is just 1/5 I. And we are done. Thanks for watching, guys.